So that brings us on to our first invited speaker of the afternoon, Dr. Marta Dudek. Marta graduated from the Faculty of Pharmacy at Warsaw Medical University in 2006. She earned her PhD from the same university in 2011, defending a thesis on solid-state NMR studies of bioactive triterpene xylosides, isolated from natural sources. Marta completed 2 postdoctoral fellowships. The first one was part of the Fugger Fellowship granted to her by the Polish National Science Centre, during which she worked in Professor Marek Poczobowski's group, improving her skills in the application of solid-state NMR experiments to solving structurally challenging problems. A second fellowship, awarded by the Polish Ministry of Science and Higher Education, took place in Professor Graham Day's group at the University of Southampton here in the UK. Here she became familiar with crystal structure prediction calculations, and since 2015 she's been working at the Centre of Molecular and Macromolecular Studies at the Polish Academy of Sciences, implementing CSP calculations and solid-state NMR studies in order to better understand the crystallization behaviour of organic molecules. Marta's talk today is entitled Understanding Co-Crystal Formation, Lessons Learned from Virtual Co-Crystal Screening Tools and CSP Calculations. Marta, over to you.
Thank you very much. So thank you for this very kind introduction. So what I wanted to show you today is what we have learned in our laboratory by looking at the co-crystallization and formation of different co-crystals of different active pharmaceutical ingredients, APIs. What we've learned from using virtual co-crystal screening tools and crystal structure prediction calculations. So this will be the main focus of this talk. So I'm going to basically show you 2 stories of 2 molecules which we were looking at during the last couple of years, linezolid and apremilast. I will give a very brief introduction to co-crystals, although I'm pretty much aware that probably most of you know why we want to look at those systems. I'm going to tell you about a bit about how do we use virtual co-crystal screening tools and what we've learned about the importance of entropy in co-crystallization. So let me start with the brief introduction to the co-crystal. So we basically defined co-crystals as solid forms which are formed by 2 or even more neutral states component, and that is to differentiate them from salts. And those components are bound together in one crystal lattice. And the important feature is that both of the parent components have to be solids in their pure form at ambient temperature for us to be able to call the final form a co-crystal, and that is to obviously to differentiate co-crystals from solvates. So why we want to look at the co-crystals? So for pharmaceutical industry, one of the major problems with introducing new drugs into the market is poor physicochemical properties of many drugs, especially water solubility, but not only, also other properties. And to give you a feeling how bad water solubility can be, we can look at water solubility of drugs that are currently marketed, well-known drugs, and compare it with the water solubility of natrium chloride, which we all know from day-to-day life. So as you can see, the difference is really huge, and these are even not the least soluble drugs. So there is clearly a field for improvement. So what we hope to gain by making co-crystals of drugs is to be able to tune physicochemical properties to improve water solubility, to make the drugs more stable, to improve their manufacturability if this is indeed the issue. We can also look at enhancing the pharmacological activity of a drug. So we can do this because we have a vast majority of different conformers which can be used to make a cocrystal. But what is often the case, what is a blessing of design of cocrystals is actually at the same time our curse, because we have such an abundance of conformers that it becomes virtually impossible to try them all in our lab. So we have to have tools to be able to select the most viable, the most appropriate conformers, so co-crystallization formers, which will form good co-crystals with our API. So this is what we were looking into when we were trying to obtain co-crystals of linezolid. This is a broad spectrum antibiotic. And so here the issue is not bioavailability of this drug, although it's not very good soluble in water, but its bioavailability is actually excellent. But it is quite toxic, and you can think of making this drug less toxic by diminishing the necessary dose, and you can do that by using drug delivery systems, and you can make actually co-crystals. We did that with other APIs, and by varying the conformer of the co-crystal, you can actually tune the release rate from drug delivery system. So that is why we were looking into the co-crystals of linezolid. So first we started with the literature review, and in the case of linezolid, there was only one patent in which 4 co-crystals were disclosed without any detailed information on their crystal structure. So each of the conformers used in this patent were hydroxybenzoic acid derivatives or benzoic acid derivatives. So this kind of prompt us to create a library of different derivatives, primarily of hydroxybenzoic acid, but not only, also with some other functional groups. But all of the conformers that we used had either carboxylic group or amide group. And we actually found that in our pre-selected set of conformers, only the ones that are marked with the green frame are the ones that form co-crystals with linezolid, whereas the other ones didn't, despite great experimental effort to obtain those co-crystals. And among the co-crystals that did form, among the conformers that did form co-crystals with linezolid, those 5 marked in yellow were really troublesome. So we had really difficult time to obtain those co-crystals. They required either very long mechanochemical reaction times or significant amount of solvent to mechanochemical formation, and even then the transformation was not complete. So obviously this prompts many questions. So why? Sorry, let me just go back. So why such so small structural changes as, for example, a difference between 3,4 dihydroxybenzoic acid and vanillic acid, which is a difference in one substituent. So vanillic acid has methoxy group instead of one hydroxyl group, and such a small structural change results in the fact that one of these conformers do form co-crystals with linezolid pretty easily, where the other one does not. So a more general question is why certain conformers are better than others, and finally, can we use virtual co-crystal screening tools to better understand linezolid preferences in terms of co-crystal formation? especially if we account for the fact that we have such a uniform library of conformers, so conformers that are really similar to each other. So for that, we used 3 different tools that can be used for Cocrystal prediction. We also added our own small tool, and I'm going to briefly introduce those tools that we are using, showing at the same time the results that we obtained. So the first tool is molecular complementarity. So this basically focuses on the molecular descriptors that are associated with molecular shape and with polarity of a molecule. So you can calculate the molecular descriptors for your API and for conformers that you consider viable, or for any conformer that you can actually think of, because that kind of calculations are pretty straightforward. And then you compare the values obtained for conformers with those obtained for your API. And if the comparison is favorable, it falls within a certain threshold, you get a pass flag. Whereas in the even if one of the molecular descriptors does not seem to match, your conformer get a fail flag. So this means that it is less likely to form cocrystals with linazolid. So when we did that for linazolid for its conformers, first we found out that the molecular descriptors hugely depend on the conformation. And this may be not that important for conformers, which are more often than not small molecules, and the conformational change, the changes in conformation does not influence the molecular descriptors that much. But for linazolid molecule, which is pretty flexible and can have different conformation, different crystals, these differences are really significant, and they translated directly into the success rate we observed for the prediction. So the blue table here shows you the results of the success rate we've obtained for different conformations of linazolid, which are given in columns, and for different method of Cocrystal preparation, they were all mechanochemical synthesis. NG means need grinding, so grinding in a ball mill without any addition of solvent, with either linazolid form 2 or linazolid form 3. And LAG means liquid assisted grinding, meaning that we use small amount of solvent given here beside LAG to form the cocrystals. And as you can see, the success rates differ significantly. So we've obtained the results ranging from 32 to almost 80%, which kind of indicate the importance of looking at the conformation of a molecule when you consider molecular complementarity. Otherwise, you can really miss some viable conformers. We also thought that this 80%, almost 80% of success rate is really, really good result, especially if we account for the fact that we have such a uniform library of conformers. So then we looked at hydrogen bond propensity, and this is a knowledge-based approach, which looks at structures deposited in Cambridge Structural Database. And what it basically does, it takes the molecule you're considering, it identifies functional groups that are present in the molecule with particular interest on hydrogen bond accepting and donating sites, and then look at the subsets of crystals deposited in the database, searching for the interactions common for this particular functional groups, and then it calculates the propensity, so the likelihood of a given intermolecular interactions to occur. So you can do that for your API and for conformers, and then you can calculate so-called multi-component score, which is a difference between the propensity, so the likelihood of formation of homodimeric interactions, so the interactions between the same molecules, and heterodimeric interactions, meaning the interaction between your API and a given conformer. And if this multi-component score is positive, is above 0, then heterodimeric interactions are more likely to be formed, and thus the cocrystal is likely to form. So if we look at the results for Linazolic cocrystals, we can see that this method also did a pretty good job. What we first of all see here is that the multi-component score that we've obtained is very, very close to 0 in the majority of cases, meaning that heterodimeric interactions are at least competitive with homodimeric interactions. And this can partly explain then why some of the conformers were so reluctant to form cocrystals with linazolid, because of the competitiveness of homodimeric interactions. We were very happy to find that there was only one case of false negative interaction, because we basically do not want to have false negative interactions. We would rather have, if we have to choose, we would rather have false negative indications. So there was only one case of false negative, false negative indication, and that was for 2,6-dihydroxybenzoic acid, but the multi-component score was really, really very tiny amount below 0. So here the overall success rate was almost 75%. So finally, we were looking at molecular electrostatic potential, and this focuses mainly on the energy of certain interactions. It also looks at the possibility of formation of hydrogen bonds, but in terms of the energy. So you basically calculate molecular electrostatic potential and map it on electron density of a molecule, and then calculate alpha and beta parameters. Alpha parameters are for hydrogen bond donating sites, beta for hydrogen bond accepting sites, and then you combine the highest alpha with highest beta values, then second highest alpha with second highest beta. You sum up these contributions, and in that way you calculate the energy of the interaction between the two molecules, and you can do that obviously for your API for all the conformers, and then you can combine the two lists and calculate the same energy for the cocrystal, and calculate the delta E value, which gives you an estimation of the energy gain upon cocrystal formation. So apart from looking at molecular electrostatic potential map, we also decided to look at lattice energies of the conformers. Why is that? It seems that this this feature should be very similar to molecular electrostatic potential, because it's also energy-based interaction. But we thought that in many crystals there are many very small interactions that contribute to the stability of the cocrystal. and these very, very small interactions are not included in molecular electrostatic potential map. So we hoped to look at the lattice energy of a conformer, so basically the energy that is required to destroy crystal lattice of a molecule, and to look whether we will find the correlation between this lattice energy and the ability of an API to form cocrystal. So first, the results for molecular electrostatic potential. So here are the minus delta E values, and the higher the minus delta E, the more likely the cocrystal to be formed. So as you can see, this method did really amazing job. All the conformers, or almost all, except one, with this one small exception of benzoic acid. But apart from that, all the conformers which obtained higher delta E values were the ones that did form cocrystals with linezolid. So finally, the results for lattice energy, as you can see, there is also a clear tendency. So the higher the lattice energy of a conformer, the more difficult is to obtain cocrystal of this conformer with linezolid, despite all these conformers having the very similar or the same ability to form supramolecular syntons with our API. So to sum up this linezolid story, what was the most important is that we found that energetic considerations were the most important in selection of viable candidates for Lin, but this was mainly because we had the pre-selected library of conformers. So we thought that hydrogen bond propensity tool and molecular complementarity are really excellent methods to pre-select conformers with viable syntons. But if you look at, if you want to have a closer look at the energetic of the possible interactions, you would do well to look at molecular electrostatic potential maps and lattice energy. But we also saw a huge benefit of using more than one prediction method, especially in such a uniform list of possible conformers. So let me now tell you very, very briefly the second story of apremilast. So here we were basically looking for the cocrystals to improve physicochemical properties, so water solubility and stability of the crystal form of linezolid. So at the time we started our investigation, there were no known cocrystals of apremilast, but there were 5 different isostructural solvates, and they all look very similar, with 2 molecules of apremilast forming a cavity in which a solvent molecule was placed. And surprisingly, even if these solvent molecules were ethanol and water, they interacted exactly the same way, without formation of hydrogen bond with apremilast molecule, even though it is perfectly capable of acting as hydrogen bond acceptor. So we treated this as a challenge. We took 4 conformers, which are very keen on forming hydrogen bond interactions in their pure crystal forms. They basically interact like that, despite the fact that they are also very capable of forming aromatic interactions. And we took those 4 conformers to form cocrystals with apremilast. But what we found was that we obtained 4 exactly isostructural cocrystals with the very same arrangement we saw in apremilast solvates. So we asked ourselves, why is that? Does apremilast not want to form any hydrogen bonds. So to kind of gain understanding of this system, we did crystal structure prediction calculations. These are the results for apremilast with picolinamide system. And what we saw on the crystal energy landscape for this system is that there is a huge energy gap between the experimental structure of apremilast and picolinamide cocrystal, which is here, marked in blue, and the next best structure. And so the gap is really, really huge. Then we looked at the lowest energy crystal with hydrogen bond formed between picolinamide and apremilast, and we found that this structure, there is one such structure here, and the formation of hydrogen bond between conformer and apremilast causes the apremilast to lose its ability to form, to pack efficiently in a crystal, and that is why it is not efficient to form hydrogen bonds. So we also looked at stabilization energies of the cocrystals, and to our surprise, these are actually enthalpies, and to our surprise, they were all positive, which means that it should not, at least in terms of enthalpy, be energetically favorable to form these cocrystals, and yet they do form pretty easily. So if you look at the crystal structures of those cocrystals, you can see that in each of them, the conformer molecule is severely disordered. And this got us to think that it may be the entropy gain that actually is a driving force to form those cocrystals. And finally, we decided to check that. These are, again, the results for apremilast and picolinamide. And you can experimentally determine the delta G of formation of a cocrystal by looking at the solubility of physical mixture and the cocrystal of a given system, and calculate the difference between the two values. And indeed, the value that we obtained was negative, meaning that actually it has to be entropy that is the driving force to form the cocrystals of apremilast with our conformers. And this also partly explains why those conformers are actually formed, because if you have a directional hydrogen bonds formed between apremilast and conformer, conformers lose their ability to have this, let's say, freedom of movement inside the crystals. So finally, to sum everything up, we found all virtual cocrystal screening tools to be like really, really good predictors of formation of cocrystals, even when having a library of very uniform library of similar conformers, although we find that energetic considerations were more important in this. So our main conclusion was that it's always a good idea to use as many virtual cocrystal screening tools as possible, as each of them gives you an insight into different aspects of cocrystal formation. And that sometimes intermolecular interactions that you can think of as more likely to be formed are more favorable because they allow molecules to pack more efficiently. And finally, that it is not only enthalpy that drives the formation of cocrystals, but you should also look sometimes at the gain in entropy, which might turn out to be crucial. And with that, I would like to thank all my co-workers and collaborators in these projects, especially Mehnaz, our PhD student. So she did most of the experimental work associated with Linazolico project. And thank you for your kind attention.
Thank you very much, Marta. That was a really interesting presentation. We have a question in the chat from Birgit at Novartis. Could you elaborate more on the details of the computations? Were experimental structures used? Were they optimized, or were these predicted structures?
Actually, rigid molecule CSP calculations for apremilast, but using different conformers. I'm not exactly sure what are which structures should be optimized and which predicted. So the structures that I showed, they are both, I mean, they are from crystal structure prediction calculations, but then they were recalculated at higher level of theory, so using DFTD. I hope that answers the question.
Thanks very much. We've got a couple of questions from Dr. Sira. Would you like to come off mute and ask your questions?
Yeah. Hello, Marta.
Hello.
Hello, Marta. Nice talk.
Thank you.
Yeah. So I have two questions. So in the apremilast, you are told that the conformer is having a disorder, right?
Yes. Yep.
I have also done few experiments in which API is having a disorder and conformer is stable. So may I know at what temperature have you recorded that data, single crystal data? Because I want to know whether it is a static disorder or it is a dynamic disorder.
So we actually looked at two different temperatures. So at room temperature and at 100 Kelvin temperature. And even at 100 Kelvin, we saw the disorder of a conformer.
Okay. So why is it so like only one component of the cocrystal is having a disorder? In some cases, it is API is having a disorder where conformer is stable. In some cases, conformer is having a disorder whereas API is stable. Can you explain this anomaly? Like why is it happening like that?
Well, I suspect this is like a property of a system. So in the case of apremilast, it is clearly the most efficient way to for this molecule to pack like that. What stabilizes that kind of packing are aromatic interactions. And it does not actually have so much conformational freedom then, because so if you look at this very molecule, you will see that there is like this angle between two aromatic rings, which makes so if you change the value of this angle, you very, very quickly start to end up with high energy regions, I mean, in terms of conformation.
Yes.
So I would say that this is because this is the reason why apremilast is not, I mean, disordered. So, and obviously in this case, this is much larger molecule that the conformers that we were using.
So you want to say it is a conformational interlock is happening in the apremilast?
Yes.
Okay. So if you observe this slide, it's just roughly a general question. The experimental structure is far more deviated with the models with the results you got from the crystal structure packing. So how far this tool is useful? Because
I mean, well, we found actually this experimental structure in our prediction. So it's not that we put it there because we know that it should be there. It was actually found there by doing the predictions, right? So it was like calculated from the prediction. So the prediction is viable. I mean, it did find the structure. We just simply observe such a huge experiment, such a huge gap in energy, which sometimes happen, maybe not as big gap as this, but sometimes you can see this happening in crystal structure prediction calculations. And this just simply means that this very one particular structure is the most likely to be formed, and the probability of forming other structures such as polymorphs is really, really low.
Okay. Yeah. So
Okay.
one
Thank you very
question.
much, Marta.
I'm sorry.
I have to move us on now, I'm afraid, just in the interest of time. Thank you again,
Thank
Marta,
you.
for an excellent presentation.